Pluto, a distant and elusive planet, was once considered part of our local planetary system. However, recent and unexpected comments from prominent astrophysicists like Neil deGrasse Tyson and Michio Kaku have brought Pluto back into public discussion. These experts have suggested that Pluto could be on a potential collision course with Neptune. But how could this happen, and what consequences would such an event have for our solar system? Could this be a remarkable cosmic anomaly, or is there something more to this looming threat? Join us as we explore the possible outcomes of a Pluto-Neptune collision. Once classified as a planet and later redefined as a dwarf planet, Pluto remains a source of fascination in the vast expanse of space. This is especially evident with the latest speculations from renowned experts. Pluto's orbit intersects closely with Neptune's, sparking concerns among scientists, including Neil deGrasse Tyson and Michio Kaku, about a possible catastrophic collision between the two, with potentially serious repercussions for Earth. But how could such a calamity unfold? Pluto's orbit around the Sun is unique, taking an astonishing 248 years to complete just one full revolution. Since its discovery in 1930, Pluto has not even finished a full orbit yet, but its unusual journey continues to capture attention. What makes Pluto's orbit even more interesting is that it is highly elliptical, diverging greatly from the nearly circular orbits of the other planets in the solar system. Even more fascinating is its tilt, which is 17 degrees relative to the ecliptic plane, making Pluto's path notably tilted compared to the orbits of other planets. This inclination and eccentricity add complexity to its trajectory. One of the most intriguing aspects of Pluto's orbit is how it intersects with Neptune's. For about 20 years during each orbit, Pluto comes closer to the Sun than Neptune, defying what would be expected based on their positions in the solar system. This raises an important question. Why hasn't Pluto collided with Neptune yet? The answer lies in the gravitational interactions of other planets. The study of Pluto's orbit began immediately following its discovery, as astronomers sought to comprehend its unique and unpredictable path. Unlike most planets, whose orbits are nearly aligned with the ecliptic plane, Pluto's orbit stands out due to its steep inclination and eccentric shape. This mystery deepened when scientists discovered that Pluto's orbit actually crosses that of Neptune. The fact that Pluto's orbit remains stable despite these complexities reveals the intricate nature of celestial mechanics. The three-body problem in space refers to the challenge of predicting how three celestial bodies, such as Pluto, Neptune, and the Sun, interact gravitationally. This problem is akin to trying to predict the movement of objects based on their initial positions and the gravitational effects they exert on one another. In Pluto's case, the three-body problem demonstrates how Pluto's orbit, along with the gravitational forces of Neptune and the Sun, interact in a complex way. Astrophysicists have coined terms such as asynchronous libration, orbital precession, and the VZK oscillation to describe this phenomenon. Asynchronous libration refers to how, whenever Pluto crosses Neptune's orbit, it is at least 90 degrees away from Neptune. This spatial separation is key in preventing a collision. Orbital precession refers to the slight upward movement of an orbiting body, which, in Pluto's case, places it above Neptune's orbital plane during close approaches, offering another protective measure. The VZK oscillation, which describes the gravitational interactions between Pluto, Neptune, and the Sun, also plays a role in stabilizing Pluto's orbit. This oscillation helps prevent erratic movements that could otherwise lead to a collision. Despite Pluto's seemingly erratic path, these stabilizing factors ensure that its orbit remains predictable over long timescales. Even though it may appear chaotic, the interactions between these celestial bodies reveal hidden patterns and rules that maintain a stable orbit for Pluto, preventing any disastrous encounters with Neptune. The three-body problem is essential for understanding how these orbits change and how celestial objects interact. By studying these dynamics, scientists gain a deeper understanding of Pluto, our solar system, and even distant stars and planets. Mathematical simulations in the 1980s showed that Pluto's orbit, despite being complex, has been stable over time. However, these simulations also revealed that even slight changes in its initial conditions could result in significant alterations to Pluto's orbit over millennia. Further investigations into the effects of Neptune, Jupiter, and Saturn on Pluto's orbit have revealed that these planets play key roles in stabilizing Pluto's path. There is a unique relationship between Neptune and Pluto. For every 2 orbits Pluto completes around the Sun, Neptune completes 3. This resonance helps maintain the stability of Pluto's orbit. Additionally, Jupiter's massive gravity helps keep Pluto from straying too close to Neptune, while Saturn's gravitational pull adds further stability. These findings indicate that Jupiter, Saturn, and Neptune all work together to ensure that Pluto's orbit remains safe and stable. Without these gravitational interactions, the solar system would be far more chaotic. Objects like Pluto could be displaced from their orbits or crash into other planets, triggering a cascade of cosmic events. As we study Pluto's orbit, it becomes clear that even what seems like an unstable trajectory can be balanced through the delicate interplay of gravitational forces and orbital mechanics. The study of these interactions also highlights the importance of continuous research in understanding our place in the universe. The study of celestial bodies often uncovers strange and unexpected behaviors, and Pluto's orbit is a prime example. The concept of orbital chaos, which refers to how sensitive a celestial body's orbit is to its initial conditions, is clearly illustrated by Pluto's path. Even small changes in its position or speed can lead to dramatic shifts in its orbit over time. Automated simulations have played a crucial role in helping researchers understand the movement of Pluto and its relationship with other objects in the solar system. These simulations model the gravitational effects between Pluto, Neptune, and the Sun, showing how slight variations in Pluto's position can alter its future trajectory. While stabilizing factors like asynchronous libration and orbital precession help Pluto's orbit remain stable, these simulations reveal that even small variations in its initial conditions can lead to significant changes. Nonetheless, despite this apparent chaos, Pluto's orbit has remained stable over timescales that span billions of years. This suggests that, despite its seeming unpredictability, Pluto's orbit follows an underlying order. Predicting the movements of celestial bodies, especially those with irregular orbits like Pluto, is a difficult task. The inherent unpredictability of these systems means that long-term predictions are uncertain. Although mathematical models have been essential in understanding and forecasting the movements of these bodies, they also emphasize the limitations of our predictive capabilities. These models are heavily dependent on accurate initial conditions, and even the smallest error can lead to drastically different outcomes. The chaotic nature of planetary orbits, such as Pluto's, serves as a reminder of the dynamic and ever-changing nature of the universe. While we have made significant progress in understanding space, Pluto's case shows how much remains to be discovered. The gravitational effects of the gas giants on Pluto's orbit provide valuable insights into the larger workings of the solar system, revealing how the position of each planet can influence the stability and trajectory of other objects. So, why have prominent astrophysicists recently raised concerns about a potential collision between Pluto and Neptune? Despite the many forces working to keep these two planets from colliding, Neil deGrasse Tyson, a leading astrophysicist, offers a unique perspective on the mysteries of our solar system, especially in regard to Pluto. Tyson, who was instrumental in Pluto's reclassification as a dwarf planet, believes that this renaming was not a demotion, but an essential adjustment based on our expanding knowledge of the objects orbiting the Sun. He sees Pluto's orbit as a reflection of how much is still left to explore in space. Tyson's concerns about the potential collision of Pluto and Neptune suggest that there are still many unknowns surrounding Pluto's orbit. Will Pluto collide with Neptune? Or is this just another instance of confusion in our ever-changing understanding of the cosmos? Only time and continued investigation will provide an answer. For now, we are left with a heightened curiosity about how little we still know about our solar system and a continued desire to explore these celestial mysteries. The possibility of a Pluto-Neptune impact challenges our conventional understanding of planetary stability, especially considering the relative strength of their orbits. Given Pluto's position on the outer edges of the solar system, far from the major planets, and Neptune's status as a gas giant with a powerful gravitational field, the implications of such an impact would significantly impact our understanding of gravitational interactions and the evolution of the solar system. To comprehend the dynamics of a potential collision, one must first consider the composition and characteristics of Pluto and Neptune. Although Pluto is considered a dwarf planet, it is made up of various substances that are likely frozen due to the extreme cold in the outer solar system. Its surface is covered in nitrogen ice, and its atmosphere consists mainly of nitrogen, methane, and carbon monoxide. In contrast, Neptune, a massive gas planet, is made primarily of hydrogen, helium, and other lighter elements, with a dense, deep atmosphere. A collision between these vastly different bodies would dramatically alter their structures and behaviors, potentially creating an event visible across vast distances. What makes this hypothetical collision particularly interesting is the role of other bodies in the solar system. While Neptune's gravity plays a crucial part in stabilizing Pluto's orbit, it is not the only factor at play. Jupiter, with its massive mass and powerful gravitational pull, also has a stabilizing effect on Pluto, preventing it from drifting too close to Neptune. Saturn's gravitational influence further complicates the dynamics of the outer solar system, making a catastrophic event between Pluto and Neptune highly unlikely. Despite these stabilizing forces, ongoing research has shown that the relationship between Pluto and Neptune is far more complex than a straightforward collision course. The gravitational resonance between the two planets, where Pluto completes 2 orbits for every 3 orbits of Neptune, creates a cosmic lock that prevents a direct collision. This resonance is crucial in ensuring that, despite their orbits crossing paths in the vastness of space, Pluto and Neptune have never collided.